Okay, so this is Wiley question number 3. This one actually took me a while to figure out, but um, I think I finally got it. So I'm going to be posting these papers up in the Facebook page, so you should be able to get them if it's not 100% clear here. I'll be doing that hopefully some point tonight. So, okay, question 3. So the question was, how many proton NMR signals, and they said not peaks, so we're not looking for splitting here. That's not what we're talking about. We're just talking about different proton environments. Okay, would you predict for the following compound? And it says, consider all protons that would be chemical shift non-equivalent, which means that they're not in the same environment, right? All right, so here is the molecule that they gave us. It's a hexane ring. It's attached to an oxygen by this bridge. And then it's also attached to a isopropyl group. And then I'm just going to add in all of the hydrogens to make it easier because that's what we're looking at. All right, so let's put in where all the hydrogens are going to be. All right, so just looking at this, I was having a very hard time figuring out what to do. So what I did is I wrote out the molecular formula, right? Which is H16O. When you count everything up. So what I did is I went to a website called www.moleport.com, and I typed in this chemical formula, and they gave me a whole list, and I was able to get the name of this molecule is 3,1 isopropyl 7 oxabicyclo 410 heptane. I don't know why it's heptane, because that's not a carbon here, but whatever. Maybe this name isn't important. The reason I went and looked for the name, because I know, okay, we're not looking for homotopic or heterotopic carbons, so actually the name is not important. You use the name when you're looking for homotopic or heterotopic carbons, but we're looking for chemical shift. So I don't think this name is necessarily important, but anyway. So what happened was, all right. So how many different chemical environments are there? So these two methyl groups are symmetrical in regards to everything else around the molecule. So these were A. This hydrogen is in a unique environment. There's no other hydrogen like it. So B, this hydrogen's unique. C. Now, these two hydrogens, I guess this hydrogen is unique because it's right next to the carbon with the methyl group coming off of it. So it's different than this hydrogen right here, which is connected or right next door to a carbon that only has two hydrogens. Now, so this is F and this is G. This is H and this is I. This is J and this one is K. Which at first I didn't really understand. Why are these different? And I think it has to do with the fact that it's hexane and it's not a benzene ring. So the answer is 11, right? There's 11 there's 11 non-equivalent chemical shift protons in this molecule. So a little explanation that I found that I hope kind of clarifies why there's 11. So in the text, see page 388 to 389. And okay, so in the text there they talk about benzene hydrogens. So benzene hydrogens are chemical shift equivalent. And so, but from what I read there, I'm going to say but maybe not. Maybe not hexane hydrogens. So they showed the molecule of the benzene ring, right? It was a 2-methyl benzene ring. CH3. CH3. Okay, and then there was these H's, H, 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 and according to them, on their graph, this had 2 chemical environments. Okay. So the 4 hydrogens, 1, 2, 3, 4, were downfield, obviously, because they were next to the pi bonds, right? And then upfield, there were the 6 methyl groups. I mean, the 6 hydrogens from the 2 methyl groups, 1, 2, 3, 4, 5, 6, because, and they're downfield because they're away from the pi bonds. From looking at this, I'm guessing that if it's a benzene ring, these hydrogens are the same because they're in symmetrical positions. But if it's a hexane ring, they're not. So hopefully that explains why there's 11. And that's it. Okay, so we'll be posting this later and I'm going to move on to the next one. Thanks.